Thank you very much. This is a joint work with Tanguy Lapeg over there. We are both PhD students at École des Mines de Nantes, and we now see how we can filter the AtMostNValue constraint with different constraints. So we illustrate this with the shift minimization personal task scheduling problem. We will say SMPTSP. It's quite long already, and this scheduling problems actually occurs when you have a set of tasks and a set of shifts, and the idea is to assign a shift to each task. But you have a few particularities because tasks are fixed in time, and a shift can only perform one task at a time. So overlapping tasks have to be assigned to different shifts. And shifts have some kind of skill requirements, so only a subset of shifts can perform a given task. And the idea is to minimize the number of shifts used in the schedule in order to reduce costs somehow. So this problem is quite simple to state, at least. In practice, it's NP hard to solve, and it has numerous applications. You can actually replace shifts by any kind of resource. It can be trucks, it can be humans, machines, classrooms, anything. So we give an illustration of this problem below with 5 tasks that are the dark lines and 5 shifts. So for instance, task 1 can be performed by shifts 2, 3, and 4, and task 2 can be performed by shifts 1, 2, 3. So this comes from skill requirements, and we see that tasks 1, 2, 3 overlap in time. So it means that we need at least 3 shifts in the schedule. You can find an optimal solution on the right. For instance, task 1 is performed by shift 2, etc. And so we decide to solve this problem with CP. For that we have a quite short model, which is quite good. We have as input a set of shifts, a set of tasks, and we assume we already have the sets, the maximal sets of overlapping tasks. And then we introduce a few integer variables. We introduce an objective variable z and a set of integer variables x to represent task shift assignments. And so actually the problem of assigning shifts to tasks turns into the problem to assigning values to variables, to integer variables. So we use an all different constraint for each maximal set of overlapping tasks, and an AtMostNValue constraint to state that the number of distinct values is restricted, and we need to minimize it actually. The initial domains can be stated as well. For the objective variable, a trivial lower bound is the size of the largest set of overlapping tasks, and trivial upper bound is the number of shifts that are available. And we assume that initial domains of assignment variables are given as input. It's computed from skill requirements. So we actually only have 2 kind of constraints, all different constraints, and one AtMostNValue constraint. Each of them is already well studied, and the idea is now to see how we can filter when they are together. So we do not introduce one more global constraint because from a semantic point of view, it's already, the model is already clear, but from a filtering power point of view, we will see how to improve the filtering of the AtMostNValue when there are some different constraints in the model. And so for that we come from the state-of-the-art propagator introduced by Bessières and others. And this propagator is, consists of 3 main steps. So first it computes the intersection graph of assignment variables. So we create a graph with one vertex for each variable, and then there is an edge between 2 vertices if and only if the 2 endpoints of variables have an unempty domain intersection. So when 2 variables share at least one value, there is an edge in this graph. Then we compute an independent set as large as possible in this graph with a given heuristic. So they suggest the minimum degree algorithm, which is very efficient actually. And with this independent set, we can filter X and Z with two rules, mainly that are rule 1 and 2. So basically, rule 1 states that the size of this independent set is a valid lower bound over the number of distinct values to be taken by X. And rule 2 can be called backpropagation. So when you have an independent set, you actually have a set of variables, and the domain induces a subset of values. And these backpropagation rules state that when you have an independent set whose size is equal to the objective upper bound, then this subset of values induced by the independent set is actually a superset of admissible values for any variable. So we can remove other variables. Other values, sorry. So you can find below an illustration on our running example. So you have domains of assignment variable, and we assume for this illustration that the objective variable is set to 1. And here the intersection graph is actually a clique. It's a complete graph because each pair of variable share at least one value. And so an independent set will has only one vertex. So we have x3 here, and it induces a subset of values 1 and 3, so we can remove other values from domains. So we start from this propagator, and we'll try to extend it a little bit to a wider family of propagators for the AtMostNValue constraint. And we introduce a formalism with 3 parameters, and the idea is to make propagators who keep the same lines, so they compute a given type of graph over those variables, then one or many independent sets with a given heuristic h, and filter variables from those independent sets and a given set of rules R. And then the state-of-the-art propagator would be AtMostNValue over the intersection graph with mean degree and rules 1 and 2. And the idea is now to change actually each of those 3 components, the graph, the heuristic, and the rules, in order to improve performance and to catch more structure from the problem. And the first step is to actually take inequalities into account in this algorithm, and this will be done by changing a little bit the underlying graph we use. And it's actually very simple. It relies on a core observation, which is the fact that whenever you have an inequality in your model of the form xi is different from xj, then you know for sure that for any solution the domain of xi and xj will not overlap because they will be different. And so there will not be any edge between I and j in the intersection graph. And if this is true for any solution, then we should not wait before removing such edges. We should not waste time during branching and filtering. And so we introduce the constraint intersection graph, which is defined as the intersection graph, but from which we remove at the beginning any edge which is associated with an inequality in the model. And so below you find on the left side the intersection graph, and on the right side the constrained intersection graph of the model. And it's much sparser actually, because there are quite a lot of different constraints. And of course the filtering can be more interesting, because once you compute independent sets, then you can find larger independent sets on the constrained intersection graph. So here we assume the domain of the objective variable was the interval 1, 3. We cannot filter anything with the default algorithm, but once we consider the constrained intersection graph, so it's really a minor modification of the algorithm. It's just an if statement somewhere in the code. We can have a much larger independent set. We can fix the objective variable and even have some backpropagation as well. And once we did this, then we can also refine filtering rules because we have more structure in this graph. And actually what we will do is that we'll use the concept of vertex neighborhood. So we used to say that the subset of admissible values was given by the independent set only, and then now it's the intersection of the independent set and the variable neighborhood we are filtering. And we can also learn some valid equalities, which can yield to stronger propagation as well. So if there is a vertex which is neighbors to exactly one independent set vertex, then the two considered variables have to be equal. So on this example, when we use the rules 3, we can learn that x2 is equal to x4, and we can contract their domain to the intersection. And clearly, all the filtering relies on independent sets. And the larger they are, the better the filtering. But it's not all. It's very important to have a large independent set, but it's also good to have different ones, because the filtering formula depends on variable indexes. And the mean degree is very good. It's fast. It has a good approximation ratio, but it's deterministic. And so we suggested to use a random heuristic as a complement to this one. And it's a very simple heuristic which computes k, a random independent set. But it's actually very efficient and a good complement to mean degree. It gives a robust propagation. And we'll now move on to some experiments we made. So we consider two data sets. The first one is from the literature, and the second one we introduced for benchmark purpose. So they have quite large instances, up to 2,000 tasks. And we used Shoko 3 for CP experiments and Cplex 12.4 for MIP experiments with default settings. And first, we would like to study a little bit the root node evaluation of the CP model. So we studied the lower bound at root node of the CP model, and the first thing we see is this red line, which is horizontal, and it shows for 100 of instances the a very horrible lower bound. It's almost 0, and this red line is actually what constraint propagation does on the classical model. So if you just let all different constraints and AtMostNValue constraint perform a fixed point, you will get a very poor lower bound, and it's extremely bad because the yellow curve actually denotes the trivial lower bound. So it's what the user gives as input to the model. So constraint propagation lead to a lower bound which is worse than the initial domain, so it's useless. But if you just change the intersection graph to the constrained intersection graph, so you just remove a few edges, then you go from the red line to the blue line, and you have a very interesting lower bound at root node. So it's very minor modification, but actually a strong impact in practice, and you can get a little improvement, 7% here, by using the random heuristic in addition to mean degree. And so what is important to see here is that the classical approach actually could not perform optimality proofs, because to get optimality certificates you need good lower bounds, and only minor modification enables to get it. We now move on scalability study, and we compared the CP resolution with the MIP resolution after 5 minutes. So in blue you have the lower bound and the upper bound of Shoko, and in red lower bound and upper bounds of MIP model after 5 minutes. And so basically we see that on small instances, so still up to 500 tasks, Cplex is very good. It can find and prove any optimal solution. And then between 500 and 700 of tasks, it starts encountering difficulties, scaling issues, but it's still quite good. And after that, so it's roughly 100,000 binary variables for Cplex, it crashes. It cannot output anything, no lower bound, no upper bound, and actually it cannot end its root node relaxation. And so, in contrast, the CP approach is much more reliable. It always outputs something, and something which is actually quite good. We have a 2% gap between the two bounds, and so it's a much safer approach for this kind of problem. And actually, this problem with MIP has already been pointed out by the OR community, and this is why they developed some meta heuristics. And so we compared our approach to those meta heuristics, which are in dotted lines. So again, in blue it's the CP results, and in red the MIP results. We see the number of optimal solutions we could get over time. And first thing is that there is one meta heuristic in the state of the art which seems not that good because it finds less optimal solution than the MIP. But actually it always outputs something, at least, even on large scale instances, and it includes lower bounding techniques as well, with Lagrangian relaxation. And the green meta heuristics, which is very good, actually has no lower bounding technique. So it finds a lot of optimal solution. It finds all optimal solutions on these benchmarks, but you cannot have any guarantee on real problems. And the CP approach is actually very good. We find all but one optimal solutions within the time limit of 30 minutes, and we have quite a good positioning with respect to meta heuristics. As a conclusion, we have a CP model which is very competitive in the OR community, and especially regarding to scalability. Because if you think about it, algorithms that are involved are somehow quite fast. Filtering algorithms are good. And all the problem structure is actually taken into account into this propagation mechanism. So this is why we can get good bounds. We don't lose anything from one constraint to the other. We have everything together. And more generally, so we have shown how to filter AtMostNValue when you have some inequalities in the model. And so for that we gave a formalism, but we suggested minor improvements to the underlying graph. We have shown that diversifying the heuristic actually had a great impact on the filtering, and we could refine filtering rules. The thing we do like with this is that it has significant improvements, which is good, but it's only minor modifications of former algorithms. It's based on state of the art, and it's based on work of the community. So we do believe that it can be maintained, it can be implemented in many servers and maintained over time. And we believe it's an important point. So thank you very much, and if you have any question, we'll be happy to answer it.
So congratulations, and you know what counts, right? Questions? Yes, Jean-Charles.
Jean-Pierre, I like very much your paper on UID. I would like to know if you think that it's possible to use your model, that is your intersection graph, the stuff you do with PHs, for some other kind of problem, not only for the memory. Do you think that it's possible to do that?
For which kind of problem, sorry?
I don't know. That's a question.
Okay. Well, we believe this problem already has quite a lot of application, and actually Indirectly, you can use this type of reasoning when you have to maximize the number of tasks you perform with a given set of shifts. So if you reverse the problem from a more operational point of view, you can take those ideas, but it's not that straightforward. You have to work a little bit on it. So, and it would be good to find the same kind of tricks for totally different constraints, but for that I have no idea, yet, at least.
Yes, please. Wait, do you have the mic? Oh, yeah.
Okay, so I'm from Embedding Research, and several years ago we conducted research on a similar problem, and we had a model where the jobs were the parents and the values of the domains were the workers, and we based the solution on some different constraints. Some different, it's like all different, but only some of the variables need to be different. So I'd suggest that I would recommend to look, we won the best CP paper in 2006, it is some different, and the best application paper in 2010 about the applications for the workers, and I think you could take a look at that because I think it's similar to things that you did.
Well, okay. So thank you. I will read those papers. I will see that.
Actually, I have a question. So, you know, you started from AtMostNValue.
Yeah.
And you made the observation that actually, you know, the min degree heuristic is A, it's not even deterministic, right?
Yeah.
So because,
you
know, between different runs.
Yeah.
And then you use randomization. And actually, did you run benchmarks just for AtMostNValue? So without, you know, the additional different constraints? Because you already get more, you know, better independent set approximation.
No, we didn't. But it's actually
Right.
very relevant. Yeah. Actually, yeah.
Your algorithm is not any longer monotonic.
Yeah, absolutely, absolutely.
Right.
When you have a randomization, it's not idempotent, not even monotonic. Yeah.
Anything else? So let's thank the speaker again.
Okay.